you, John. It's nice to be here. I'll get this next slide. Yeah, don't actually get to speak in the IT very often, despite being a fellow. I'm going to tell you about what's next in memory safety. Some things have already been alluded to. Thank many sponsors. What's the motivation? Well, memory safety is a major challenge. Year on year, roughly 70% of all our vulnerabilities are memory safety related. So this is a quote from the previous director at the NCSC. We're seeing similar things from Microsoft when they analyze all their vulnerabilities. It's not just their problem. Google seeing, it seems this 70% number just keeps coming up again and again. So let me just quickly tell you what is memory safety by giving you an example. And forgive me, I'm talking at the moment about more sort of application class vulnerabilities. I realise this is more of an IoT event, and I encourage you to go and see a talk later on in the programme by David Chisnell from SCI SEMI, who's going to be talking about exactly the same sort of technology, but in the IoT context. So forgive me giving a lot of application class examples. Anyway, here's a very simple example from the Heartbleed bug that impacted the TLS security protocol used to secure transactions on the web. Okay? And one of the things that was a component of that is to keep the connection alive. We have this heartbeat message that goes backwards and forwards between the web browser and the server. And so let's explain this in XKCD comic. So, the client says, so I can't actually read that, which doesn't help. Say potato, and, the server says potato. Now say bird, it's 4 letters, it says bird, and then the client gets a little bit more clever. It says, server, say hat. It's 500 letters long. I mean, this is kind of unbelievable, right? But this is a genuine vulnerability that impacted banks. It allowed you to impersonate banks. It allowed you to do fraudulent transactions. It allowed all sorts of stuff. And you just got a buffer over read error, where not only did you get hat, but you got the rest of the buffer, including secret key information and all sorts of stuff. I mean, it's just ridiculous. So that's nuts, right? And the trouble is, this is happening again and again and again. We've seen something very recently with WebP library for image decompression. Similar sort of problem. I'll tell you about that in a minute. So the question is, how can we do better? Well, there's a big push to use more memory-safe languages, and I thoroughly encourage them, and I am not trying to denigrate that at all. I think it's a great initiative. Rust and other languages, absolutely. Particularly new code makes so much sense. But we do also have a vast amount of C, C++ code, a lot of other code written in other languages that are not inherently memory safe. And moreover, there's quite a lot of Rust code gets written in unsafe Rust, and we'd like to be able to make that memory safe. So our approach is to recompile your code and basically add a new data type, which I'm going to explain in a minute. We believe we can then make your C++ code more efficient, more secure rather, and also make your Rust code more secure. So let me tell you about the technology. So we're going to be doing a little bit of a technology deep dive, and then we'll look at how we've evaluated this and what the sort of government level response and various other things has been. So CHERI is a modern capability architecture. We introduce a new data type into the system, a bit like introducing floating point, but here we've got a data type that is a reference to memory, if you like, a pointer, but it is more than a pointer. It has bounds and permissions and provenance, and it has key security requirements from the instruction set, in particular guarded manipulation of capabilities. So in particular, you cannot increase your bounds or your permissions. The hardware just doesn't allow it. And in fact, we end up doing a lot of formal verification work to make sure those guarantees are obtained by the hardware. Then when we come to implement it, we take, we've got our integer registers, so this is the most technical deep dive slide. We can also, obviously store things in memory. We're going to add this additional capability metadata to our registers. We're going to add them to the program counter so we can bound accesses to code. So for code pointers, we've got tagged memory, which is very important for validity and provenance. And we add these new instructions to do bounded manipulation of capabilities and to access capabilities and memory through capabilities. And then, we reuse existing encodings where we can. We have a default data capability which we can use for legacy code. And then various systems mechanisms. And capabilities also live in memory and in caches and so on. Okay, so let's come back out. What does that mean for software? I wish I could make this bigger because I cannot read my own slide, which is just ridiculous. Okay, we get integrity and provenance properties. So we can guarantee the integrity of our pointers. You can't just get a pointer coming out of thin air. We've got bounded access to data, and that resolves a lot of problems. We've got monotonicity, so this idea that you cannot grow your bounds and permissions. We've got the permissions themselves, so these are obviously obvious things like read, write, execute, but also can you store a capability there, which turns out to be very important when we're sharing things between compartments. And through this, we get very strong spatial and temporal memory safety. One thing to bear in mind here, we get that we could just recompile code. The vast amount of code just recompiles, and then it becomes memory safe. Okay, you just don't need to do anything at the software layer. We can also adapt the software a bit to break things up into compartments, and that also gives us really fundamental security properties because we can reduce the attack surface. So let's just look at that in a little bit more detail. Richard Grissenthwaite talked about POA2, which helps with doing process-based compartmentalization. One key thing about CHERI is we can be substantially more efficient, at least an order of magnitude, if you want to compartmentalize things. And we're using compartmentalization today in things like web browsers. Every tab in the web browser is in a separate compartment. But we'd also like to be able to render every image in a compartment and so on, and have very fine-grained compartmentalization. And the actual CHERI hardware enables these mechanisms. So let's talk about evaluation. So a lot of evaluation has been done, and we've had a lot of great interactions with industry. So very substantial report undertaken by Microsoft. They looked at all of their 2019 vulnerabilities, and they asked the very hard question, if they'd used CHERI, how many of these vulnerabilities would they have not needed to even patch? Okay, so CHERI completely solves the problem. And they concluded that 2/3 of all the vulnerabilities would have just evaporated, which is quite an amazing result. We've also been lots of studies. So this is a small pilot study, so small company, Capabilities Limited. They took a Linux base or a Unix style desktop stack and just ported 6 million lines of code over about 3 months. And they concluded that they needed to make a few modifications, things like memory allocators, a few bits and pieces, but then got an amazing mitigation rate. More recently, Capabilities Limited and University of Cambridge have been looking at the grand challenge of the Chromium browser. So Chromium is an enormous code base. It's around 46 million lines of code. It includes 7 just-in-time compilers. I mean, it is ginormous. But the interesting thing is they took a fork of the version of Chrome, did the port. It took one person, year and a half. A lot of it was actually in the just-in-time compiler stuff that need to be taught a little bit about these new memory protection mechanisms. And then we looked back, because we'd forked the code base, and we said, well, what vulnerabilities had occurred in that 18 months that is, are now published and Google have patched? And there were lots of them. And the great thing is we realized that CHERI just mitigated them. This is a great example. This particular CVE was impact on the WebP library that Google uses. And this is first-party code for Google. It's third-party code for Apple and Microsoft. It resulted in zero-touch, zero-day vulnerability in iOS. So it's a really big deal. And for that library, we didn't need to change any of the code at all, and we got 100% mitigation. Okay, so this is a very effective approach. So, yeah, taking things from research out into commercial deployment has been a big challenge. And I'm pleased we've had a lot of support from various government agencies. The early work back in 2010 was funded actually largely by the US, by DARPA, and we did initial work on a MIPS-based platform because back in 2010, this is before ARM had a 64-bit processor, it's before RISC-V existed, and so we used MIPS. Then under the Digital Security by Design program, we had an amazing initiative, lots of industry involved. ARM did an amazing job of producing the Morello prototype, so CHERI on ARM on a serious desktop system. We also, in the university and with others, have been working on CHERI for RISC-V, and we've now got CODASIP have announced their CHERI RISC-V core, and also SCI SEMI, through initial work with Microsoft, have got their Chariot core, and more of that in David's talk later. And we're going through a standardization process at the moment for the RISC-V, and we're hoping that lessons learned from that in simplifying the architecture can then lead back into a CHERI for ARM for a final end product. So we've got things at various scales, so the superscalar out-of-order core from the ARM Morello, so this is a serious high-end system, GPU, 7-nanometer process, really big deal. We've got the CODASIP design, and we've got the Chariot design, originally from work at Microsoft, now being championed by SCI SEMI and Low Risk and Google and others. The standardization stuff is going well. It's a hard push. A lot of what's ended up in this RISC-V open instruction set architecture is basically getting feature compliance with sort of ARM and x86. So it's kind of well understood stuff. We're really pushing the boundaries here, pushing a new technology, and that's been challenging, but also, we're getting traction. I also occasionally wear a hat at Capabilities Limited. We have an open source 64-bit core that's supported by the Open Hardware Foundation. And we're aiming, I don't think we can't announce it yet, but we have a new project started that will do a lot of DV and get this into a product-worthy form that people can use. Through CODASIP and others, we've set up they've set up the CHERI Alliance, so this is to get industrial and technologists together, and we've got a large number of people joining that, which is amazing. There's the CHERI Tech event as well in November, if you're interested in this stuff. And let's sort of start bringing things to the close. So we've received quite a bit of recognition, as you can imagine, quite a bit in academia. So it's great that actually we swept the awards for IEEE Security and Privacy. We got both the sort of Test of Time Award and the Best Paper Award, which was announced recently, which is pretty good. We're also seeing things coming out of government. So there's this Five Eyes report that is really trying to push industry to build much fundamentally more secure systems, and they recommend CHERI as the secure hardware foundation. And under the previous administration, we saw things coming out of the White House, also pushing technologies like CHERI, and CHERI is also part of the National Semiconductor Strategy. So let me wrap up. So there's some QR codes, which I gather from John people might be a bit nervous about. So there's a sort of thought piece that you might be interested in from that we published with various industrial players, some of whom are in the audience today. a thought piece through the ACM, so that's quite a good sort of high-level read. There's also, award-winning work on how do we make C, C++ code safe. Okay, so let me wrap up. CHERI provides hardware with new semantic knowledge of what the software intended. Okay, basically today when we compile code for our current machines, memory references just turn into integers, and you don't distinguish between integers and pointers. And we resolve that problem. That fundamentally mitigates a lot of problems. So we get, very efficient pointer integrity and bounds checking. It eliminates buffer overflows, buffer overreads, just fundamentally. It's really important to stress this is completely deterministic, non-bypassable. A lot of other schemes out there are much more statistical in nature, including MTE that Richard Grissenthwaite mentioned. And the trouble with anything statistical is it's bypassable. Maybe it may stop the attacker a little bit, but it won't fundamentally stop them, whereas CHERI will. It also provides us incredibly powerful and efficient compartmentalization, so we can break software up. We have a scheme to just automatically compartmentalize all libraries, for instance. And this fundamentally reduces the attack surface in your system. And we also get a big performance win, which is always nice, both security and performance, over process-based compartmentalization that's used in things like Chromium. It's used in iOS to separate things out. And then we're working with industry and the open source community. And really tying in with Charlie's talk earlier, how do we sell security rather than performance? I think this is our big challenge. So here we've got a technology. It comes with a very small cost. 1 or 2% memory overhead is the main cost. We've demonstrated you can actually build this in a high-end silicon node for a high-end processor. So we've got rid of many of the unknowns. But I just leave you with this thought. I think one of the biggest challenges we have is basically localized cost optimization. A lot of industry, people selling hardware, they're cost optimizing their part. And it's often the people selling the hardware are not feeling the pain of the security problems. So we've got that lack of connectivity in the objective of making systems fundamentally more secure. And I'm just an academic, so I'm sort of reaching out to you. How do we fix the business models so that we really can do better? And the sort of last thought is, will we go down in history as the first society that won't save itself because it wasn't cost effective? So I'll leave you with that thought.